Hello everyone, welcome to week 7 where we're going to talk about nutrients. I've got about 28 slides to go over some definitions and why nutrients can be an issue, behavior in streams, biological processes, and then diel cycles more broadly than just for nutrients, and then monitoring and quantification challenges dealing with non-conservative parameters such as nutrients. So first, what is a nutrient? It's a substance that can be metabolized by an organism for organic synthesis. And so these are the top elements by mass, the elemental composition of plants. And so we saw this picture previously of a wheat crop growing and a flux tower, an eddy covariance system measuring the flux of water and carbon between this crop and the atmosphere. And we see photosynthesis occurring here where carbon dioxide and water are combined with energy from light to produce simple sugars and oxygen. And so in this case, actually, water is one of the more limiting constituents that the plant needs. But as far as the elements, it is, so carbon, oxygen, and hydrogen are in ready supply from the atmosphere. But when we get down to nitrogen, plants have to get that from the soil, and the same for potassium and phosphorus, and those three along with sulfur are often what is most limiting for plant growth, and that's why we see this NPK often on fertilizer bags, and it's nitrogen and phosphorus that we're most interested in for water typically. First, to talk about some of the concerns with nutrients from a toxicity perspective, nitrate can be toxic for infants because of a condition called methemoglobinemia, or commonly called blue baby syndrome, where the nitrate is actually converted to nitrite in the stomach, and babies lack the enzyme to deal with this, and it binds to the hemoglobin in the blood and reduces ability to carry oxygen, and so results in a blue or gray hue, often showing up around the mouth first, that is an indication of low oxygen in the body, which can obviously be a problem. There's also some indication of increased cancer risk, and the drinking water standard for nitrate is set at 10 milligrams per liter, and that is for the methemoglobinemia risk for infants and pregnant mothers. Ammonia has issues with toxicity for aquatic life. And so this was a big problem with wastewater treatment plants early on, and is something that has been dealt with largely very effectively. And it is pH dependent. So because of the way that the ammonia is an acid, and so because of the way that it takes on and loses that additional hydrogen to make it NH4, the toxicity changes with different pHs. Is just kind of a side note there. But so to step back to what the concern is with nitrogen and phosphorus from an environmental perspective, eutrophication is something that we're commonly worried about. And so from that first slide with the wheat crop on it, I said that nitrogen and phosphorus were listed as limiting for terrestrial plant growth, and these two elements are those in streams that are most typically limiting. And we'll talk a little bit more about reduced oxygen effects, and you can get these swings in dissolved oxygen over the course of a day because of these algae, and we'll talk more about that. Recreational impairment is something that can happen with this excess algae growth. Reservoirs that look like this, people don't want to swim in those, and then fishermen don't want to fish in streams that look like this, and there can be a number of economic impacts both from these recreation effects as well as for infrastructure and cities and towns that get their drinking water from from surface water can really have problems as a result of excess new algae growth. One, just from a treatment perspective, trying to filter that out, and then two, as a result of the chlorination disinfection byproducts that react with the soluble organic material in the water and create those carcinogenic disinfection byproducts. So there are a lot of reasons why excess nutrients can be a problem, and I mentioned before in Montana we have about 1,000 assessment units that the DEQ has broken the state's waterways up into, and phosphorus and nitrogen are in the top 10 for impairment parameters for a high percentage of those waterways. And here's a list of the suggested causes of those. Agriculture on the list for a number of these, but there are also important urban sources and others coming off of various types of non-point source pollution. So thinking back to the beginning of our understanding of how nutrients work in water is a pivotal paper in Science in 1974 by Schindler, where they went in and they split this lake in half and they fertilized half of it and left the other half, and saw this just incredible response in the primary productivity of the fertilized side. And as a result of that, there was an increased awareness about the fact that it's nitrogen and phosphorus that can cause these excess nutrient issues, and that are causing ultimately the hypoxia in the Gulf of Mexico, which is the dead zone, as I'm sure all of you have heard about. And this is the size of that dead zone over the years, a real problem for the fishery in the Gulf of Mexico. And so the Clean Water Act had narrative, and the laws that many of the states enacted to administer the Clean Water Act had narrative water quality standards that say things like state waters must be free from substances that will create conditions undesirable with undesirable aquatic life. And because of the fact that interpretation of a statement like this can be very subjective, there's a need for numeric water quality standards. And the problem is that it's similar to sediment in that nutrients in streams are critical as the food to grow the algae, and that is at the base of the food chain that fish and other organisms, macroinvertebrates, rely on. And so some amount of nutrient transport by streams is natural, and so coming up, and the amount that is natural varies based on a number of attributes that are fairly well represented by ecoregions. So similarly to the way that reference sites are broken down within ecoregions in Montana, the nutrient reference sites are on the same, laid out in the same scheme, because we do expect different numbers for different areas. Figuring out what is natural for nutrients is an onerous process, and so in 1998 only 7 states had adopted any numeric nutrient standards for protection of environmental quality against nuisance algae. That number had increased quite a bit by 2008, and Montana is doing some really incredible work on this front and has numeric nutrient standards in place at this point. So thinking about the nitrogen cycle, we've got 78% of our atmosphere is nitrogen, but it's tightly bonded in these triple bonds among nitrogen molecules. And so the only way that has been available to plant life, this huge reservoir, is through fixation by nitrogen fixers. And then there's cycling within the soil, and then there are losses through leaching. But effectively in the early 1900s, Fritz Haber came up with a process to fix nitrogen out of the atmosphere using high pressure and a lot of energy to get ammonia into gas. And then Carl Bosch came along later and industrialized that process to make it possible for us to effectively add another component to the nitrogen cycle, where Haber-Bosch nitrogen is where the vast majority of our nitrogen fertilizer comes from. And as a result of that, humans have dramatically changed the global nitrogen cycle. In this plot from a paper by Ersman that's available in your supplemental readings, we see the world's population growing and the global inputs of nitrogen in the form of Haber-Bosch fixed ammonia, and we can see that there's a strong correlation here between after World War II, when Haber-Bosch nitrogen went up and the world population shot up, and they estimated in that paper that 48% of the world's population are fed by food grown on Haber-Bosch nitrogen today, or in 2008 rather. So if we think about this, this human effect on the global nitrogen cycle, we've got a nitrogen fixation plant, and we can think about this nitrogen cycle also in terms similar to how we've been looking at for the global hydrologic cycle, in terms of the size of these pools. And the 98% of the nitrogen on the planet is in the lithosphere, and most of the remaining is that 78% nitrogen in the atmosphere. So we're really dealing with fairly small numbers typically of these labile portions of the nitrogen cycle that we've affected so dramatically. In terms of phosphorus, the majority of our phosphorus comes from being mined out of various minerals, and then so nitrogen and phosphorus are transported around the country and then are applied to farm fields for production of food for humans and food for livestock. And then the result, in the case of human waste, a lot of times by design, we treat it and take a lot of the nutrients out, but then put our wastewater with some nutrients still in them back into our surface waters. And then in the case of livestock, we've got a lot of manure production, especially in the case of confined animal feeding operations. And so there are risks to water quality here with the ultimate waste products from animals, and there are risks to environmental quality with inefficiencies in fertilizer application, fertilizer that gets added and then doesn't make it in to these crops that they're intended to. And the result is this picture that I keep showing of the excess algae in streams. So consistent with the theme from the hydrology section that we keep touching on is that overland flow and subsurface flow are two important pathways for nutrients. And so overland flow can again be both particulate or soluble forms of nutrients, where nutrients that move down through the soils and then ultimately to groundwater and streams through that subsurface pathway are the dissolved fraction. And so examples of direct inputs from overland flow to surface water, or pipes in this case of a municipal wastewater treatment plant, is one. Municipal stormwater runoff, there are definitely nutrients in that, both from people fertilizing their lawns, and then particulate just from things like grass clippings or pet waste. Runoff from feedlots or dispersed pasture grazing can definitely contribute nutrients. From animal waste, or runoff over the surface from crops, or irrigation water that then ultimately returns to the stream. Groundwater, this is a map that shows the highest nitrate concentrations from our private well testing program across Montana, and we see some really high numbers in some places across the state. Natural background we would typically expect to be less than 2 or 4, depending on where you're at, and the drinking water standard again is 10, and we've got places in central Montana that are up above 50, and here in the Gallatin we've got places that are above 15. And in the Gallatin we definitely have places where disposal of wastewater, both from municipal treatment systems and well and septic, are causing some issues. So we can see this septic density map increasing from 1970 to 2009, and septic systems are very basic in the treatment that they accomplish. They have primary treatment in the septic tank, and then they rely on treatment in soil to remove a lot of the remaining constituents. And they're not, traditional septic systems are not designed to remove nitrate, actually. They rely on dilution in groundwater for that. And that's why they have a mixing zone associated with them. And when you get really high concentrations of septic systems, that dilution doesn't always happen. Similarly, in Montana's capital, Helena, there has been a big increase in the number of septic systems, and there's potentially some issues associated with leaking sewers as well. And this paper by Botter and Drake shows increasing concentrations of nitrate from 1971 to 2000 in that valley. And so these are examples of septic sources for groundwater. Another example is in my PhD watershed, the Judith, that we've seen some data for. These are primarily, so these tan areas are quaternary gravels that look like this and have relatively thin soils over the top of them, where wheat is cultivated primarily. And because of these really thin soils, when water and solutes move down through the fine stuff up here, the clay loam, there's not much holding the water and nutrients from moving down through the gravels into the shallow aquifers. And Montana Department of Agriculture published a study in 2009 showing the mean nitrate concentration in these aquifers of 13 and a high in that study of 38, and we found numbers up over 50 in the work that we're doing. And in one of the wells here on the Moccasin Terrace, they've shown an increase from about the drinking water standard to about double the drinking water standard in the past 15, 20 years. So this is a real issue for the people who have private wells out here and are drinking and relying on that water for their domestic supply. And then indirectly, groundwater, the high nitrate concentrations in groundwater impact surface water. Here we see a simple graphic from USGS showing a stream gaining water from groundwater. And in the Judith, this is an example of one of the springs that is discharging water out of those gravel aquifers with high nitrate concentrations into a surface stream. And these concentrations in a couple of these creeks here are close to 10 milligrams per liter in places, which is just incredibly high for surface water. So I've focused on nitrogen largely up to this point. Phosphorus is also very important, as I had mentioned, and phosphorus behaves very differently from nitrogen. While nitrogen has a complex cycle that is primarily, that has a number of soluble forms, phosphorus is dominantly associated with sediment. And we can see that here in there's a paper that talks about the distribution of phosphorus in a fish pond, and 99, if you took a cross section, a 1 meter cross section going down through the pond, 99+% of the phosphorus is in the sediment. And of the remaining portion that's in the water column, the vast majority of that is in particulate. It's associated with particulate in suspension. So phosphorus really likes to be bound to sediment. And that's why in the paper that we read on the turbidity measurements in the Utah watershed, in the Little Bear, why turbidity and suspended sediments were a good surrogate for total phosphorus. So I've said that nitrogen and phosphorus are most commonly the limiting nutrients in a stream system, and that means that when you apply these two nutrients, you remove the limitation on algae growth and you get this excess algae growth. There can be co-limitation of nitrogen and phosphorus, or one of these could be much more limiting in a system. You might have plenty of phosphorus in a system and not enough nitrogen, so it's really the nitrogen that's limiting, or vice versa. And in general, phosphorus tends to be limiting in freshwater systems, and nitrogen tends to be limiting in marine systems. And there are a few different reasons for that I'm not going to go into, but we can figure this out with a nutrient bioassay. And so if we take water from a lake or a stream that we're interested in, and then we have a control, and then we add nitrogen to one and phosphorus to another, one possible outcome is this, that you get increased algae growth in the bottle that has the nitrogen added. in that case, it was nitrogen that was limiting algae growth. The other possibility is that you get increased algae growth in the one with phosphorus, and then we could also do, and in that case, phosphorus was limiting. And in some cases, they could both be co-limiting, and you would actually need to add both of them to get dramatic increased algae growth. A concept that's important to think about with nutrients is what's called the nutrient spiraling concept. And I've drawn a graphic, a cartoon of that here, where we can think about soluble nutrients coming downstream and then being taken up by plants, and then those plants senesce or die and are degraded, and the soluble nutrients are released again, and then they're taken up a short distance downstream and they're spiraled downstream like this. And so following this conceptual diagram, we would then see a decrease in concentration and then an increase as it's released, and so on like this, right? Conceptually following the spiral. But we don't actually see these changes in concentration because this oscillation is happening continuously at all points in the stream. And so soluble nutrients in a natural stream system with really low concentrations of nitrogen, soluble nitrogen and phosphorus are going to be taken up very readily. Those nutrients are not going to make it far downstream before the plants in the stream are going to gobble them up because they're starving for those nutrients. In polluted systems, things start to behave a little bit differently, and you can actually saturate them, and that's what you've done typically when you have really high concentrations of nitrate, for instance. But this concept can translate into is related to what we see with diel fluctuations. And so this is the paper that you're going to read for this week, and we can see that so these grayed areas, this is a 48-hour experiment, and these grayed areas are the nighttime, and then the lighter areas are daytime. And on this first y-axis, we've got algal pigments, and that's the solid line here. And then on the secondary axis, we've got dissolved inorganic nitrogen and soluble reactive phosphorus. And so the solid line is the algal pigments, and the dashed line is dissolved inorganic nitrogen, and the dotted line is the phosphorus. And we can see that the algae is the highest during the daylight, and that the nutrients are lowest, are highest at night. And so there's an inverse relationship. When the algae goes up, the nutrients go down. Algae goes down, and the nutrients go up. And so this makes sense if we think about it, that the activity of the primary production, the plants and algae in the stream, is all mediated by the sun. So this is photosynthesis is occurring to increase the biomass of the algae, and in so doing they need nutrients, and so they take those up, and we have that opposite swing. And this is the same diel fluctuation happens for a number of parameters in streams. So higher during the day in some streams. This isn't constant for all streams, but if there's very much primary productivity in a stream, we're probably going to see these phenomenon. That photosynthesis is higher in the day. That's obvious. There's sunshine. Dissolved oxygen is higher because we're going to have this photosynthesis occurring from the algae. pH is going to be higher because of increased concentration of hydronium ions, and I'll talk about that on the flip side in just a second. Algae pigments are going to be higher. Temperature is probably going to be higher in the day, and in some cases anionic metals that sorb to the substrate, and this is because of displacement by the higher concentration of hydronium ions, that you can bump things off of the substrate. And I'm not going to go into that, but it's a pretty interesting component as well. Higher at night, on the flip side, are the nutrient concentrations, because the plants aren't as actively taking them up. Carbon dioxide is higher at night, and this is because respiration of everything in the stream continues at night, but there's not photosynthesis taking that carbon dioxide up. And so carbon dioxide goes up, which is converted to carbonic acid, which reduces the pH. And so that's the, lower pH means more hydrogen ions, a higher concentration of hydrogen ions. And so that's because hydrogen ions and hydroxide ions are in equilibrium, that's why we see this opposite effect here. And then cationic metals that sorb to sediment can be higher at night because this higher concentration of hydrogen ions in the solution bumps these cations off of the substrate. And so I have some other papers if people are interested in that. We could talk about that in one of the next weeks. But these diel swings in a number of parameters are critical for us to understand our aquatic systems, and all of it is mediated by the rotation of the Earth, and so the changing amount of solar radiation hitting us on a given hour of the day. So I want to circle back around to hypoxia in the Gulf of Mexico, and this is there's some great USGS references, and this is a map showing the degree of hypoxia in the Gulf. And this is a serious issue, as I mentioned, for the fisheries in the Gulf of Mexico. And to think about why this happens, let's talk about biochemical oxygen demand, or BOD, which is the amount of oxygen required by microorganisms to break down organic matter in a water sample. So detritus, might think about leaves or other things that are dead on a forest floor. That's a common type of organic material that needs to be broken down. And so if you've got your little microbes in your water sample here that are going to work to break down that carbon, they need oxygen to do that. And so we measure that with biochemical oxygen demand. And so this is a graph of the BOD, or the cumulative biochemical oxygen demand over time. And so a lot of the stuff is really readily broken down, and it happens you might have heard of a 5-day BOD, and that's because at 5 days you've broken down the vast majority of the material, and then the rest of it is really slow, and so this line flattens out, and there's less chemical oxygen demand after 5 days. This is important if we think about a wastewater treatment plant that we're dumping all kinds of organic material into, and the plant is treating that and then discharging that water to surface water. We can think about time and distance downstream as being similar because it takes time for the water to travel, right? And so a related graph here is the dissolved oxygen concentration in the stream downstream from the wastewater treatment plant outfall. And so because the bugs need this oxygen to break down that detritus that's in there, or the human waste, you get a dive in dissolved oxygen as you move downstream. And then as the things get broken down and there's less oxygen demand on this part of the BOD curve, it'll come back up. And so before we're doing a good job with our wastewater treatment, we would get these big dives in DO downstream from the outfalls, and you'd get big dead zones. And these dissolved oxygen dives still happen to some degree downstream from wastewater treatment plants, but it's a much less prevalent issue than in the past. So thinking about the controls on dissolved oxygen in streams, salinity is important, but as far as freshwater goes, the salinity is so low that it's really not important compared to the others. If you're talking about seawater, then salinity would be important. The rate of O2 coming in from the atmosphere, which is both pressure and concentration of O2, and we can think about that. We know that we've got a pretty constant percentage of oxygen in the atmosphere at about 21%, but as you increase in elevation, the pressure goes down. And so at high elevations, we have low pressure, and at low elevations, we have high pressure. And actually, you will all note that this graph has the independent variable is elevation and should be on the x-axis, strictly speaking. But conceptually, we know this because when you go to high elevations, to Everest or on climbing expeditions, people suffer from pulmonary edema or other physical problems from lack of oxygen. So high elevation, low pressure, and that means that at higher elevations there's less oxygen to dissolve into streams, and we do see that. Water temperature is important, and a lot of you are probably familiar with this, that the amount of oxygen that is possible the saturation concentration of oxygen in water decreases with increasing temperature. So this doesn't necessarily mean that you have less oxygen, but overall you can have less. So when the temperatures of water get high, so So when the water temperature is close to 0, then you can have 14 point some milligrams per liter of oxygen, whereas if you heat up to 20 degrees at room temperature, then you're down to the maximum oxygen being at about 9 milligrams per liter. So here is some data for dissolved oxygen for a creek in Texas, and we see definitely a diel fluctuation here. These are over the course of days, and if we plot temperature at the same over the same period in that stream, then we can see that the lows and the highs occur together. So if we're thinking about the explanation for this DO, do you think it could be temperature? No, if we think about it, it can't be, because you would expect to see the lowest temperatures occur at the same time as the lowest dissolved oxygens, and so those are probably happening at night. And at those low temperatures, if the dissolved oxygen changes were driven by temperature, then it would be an inverse relationship, right? And at the highest temperatures, you'd see the lowest dissolved oxygens. But we see them tracking together. There's a positive correlation, and so this leads us to believe that it's one of those diel fluctuations from algae growth in the stream and the photosynthesis. So the USGS has some great resources on this. Unfortunately, right now, the web page is down for the USGS, but I think we have a PDF of some of this that we can put up for you guys to look at. Huge loads of nitrogen to the Gulf of Mexico outlined in there. The same with phosphorus, and they break it down by causes as far as land use, and by causes as far as which states. And 75% of the nutrient load to the Gulf comes from 9 states in the Midwest associated with cropping. And their animal waste is also a big component of this. And they use a number of gauging stations to produce these numbers of flux of nutrients to the Gulf. And it's important to note that we're seeing dramatic cutting in the funding for these gauging stations, which really cripples our ability to understand what's happening with nutrients coming off the landscapes and our water quality. So the last thing I want to touch on here is just the fact that because nitrogen and phosphorus are taken up by plants and can change phase between these various species of nitrogen, they are non-conservative. Salts in general, sediment I said it was conservative, obeyed conservation of mass moving downstream. Salts in general are largely conservative as well. Nutrients are not conservative, and so we have to think about that because we basically end up getting temporary storage of nutrients in algae growing in the streams. And we also get these fluctuations that and the diel concentration changes. So when we think about quantifying how much nutrients are moving past a place on a stream, it's not always as simple as measuring the concentration and the amount of flow upstream and that equaling the amount of concentration and flow downstream plus what came into that reach, because we have these processes going on. And that is one of the underlining concepts from the paper for this week that you'll read.